Hello. Today, in this video, we will show how to derive the Friedmann and Raychaudhuri equations of Newtonian and relativistic cosmology. We will discover that they are identical in both theories. In other words, there are no general relativistic corrections to the equations of Newtonian cosmology. This is quite a surprising fact. It was first discovered by Milne McCrea way back in 1934. After deriving the equations in these theories, I will explain the reason that lies behind this result. We make two assumptions about the universe. First, that it is homogeneous, that is, every point in the universe at a large scale looks like every other point in the universe. And secondly, that it is isotropic, that every direction looks like every other direction in the universe. We will start by investigating the three-dimensional spaces which are both homogeneous and isotropic. Now there will be three of these, and there's a very nice geometrical construction of each. So we're going to start off with the three-sphere, S3, which we're going to embed in R4 by the condition S3 is the set of vectors in R4 such that x0 squared plus x1 squared plus x2 squared plus x3 squared plus, that's enough, is equal to kappa to the minus 2. So this is just a sphere of radius 1 over kappa. We have the Euclidean metric on R4. ds squared is dx0 squared plus dx1 squared plus dx2 squared plus dx3 squared. So from this equation, we end up with x0 dx0 plus vector x dot dx is 0, while I'm writing vector x as x1, x2, x3, and therefore dx0 is minus x dot dx over x0. Now I substitute that into here and I find that the induced metric on this sphere is x dot dx squared over x0 squared plus dx squared. Right, let R be the modulus of x. So then x dot x is r squared, and therefore x dot dx is r dr. So this gives me ds squared is r squared dr squared, that's that. x0 squared, get from here, that's kappa to the minus 2 minus r squared, plus this thing here, which is just the metric r squared, dr squared, d theta squared plus sine squared theta, d phi squared if we introduce polar coordinates. So that's just the Euclidean metric on three-dimensional space. That's that there. So that's dr squared over 1 minus kappa squared r squared plus r squared d theta squared plus sine squared theta d phi squared. We can understand this in terms of an SO4 rotation. The group SO4 will preserve this sphere here, and it will act transitively. That is, every point on the sphere S3 can be mapped from every other point. Now, the things which are left invariant once you've mapped to a particular point are just going to be the rotations about that point. So we have S3 is the space SO4 over SO3. So we can see that this space is both homogeneous because every point on the sphere looks like every other point on the sphere, and it is isotropic because if you perform an SO3 rotation, then the 3 sphere remains unchanged. Now we can perform the same calculation with the following. H3 is x in R13 such that minus x0 squared plus x1 squared plus x2 squared plus x3 squared is minus 2. And the metric is ds squared. I wrote R13 to indicate that we're looking at a Lorentzian space here. dx1 squared plus dx2 squared plus dx3 squared. Well, in this case we get dx naught is plus x dot dx over x naught, and ds squared is going to be minus x dot dx squared over x naught squared from there plus d vector x squared. So that's going to give me, again writing x squared is r squared, I'm going to get minus r squared dr squared over kappa minus 2 plus r squared plus dr squared plus r squared d theta squared plus sine squared theta d phi squared. So that gives me dr squared over 1 plus kappa squared r squared plus r squared d theta squared plus sine squared theta. The interpretation of this is of hyperboloid, a two-sheet hyperboloid, in a 4-dimensional Minkowski space. We're really interested in a simply connected component of this. Now I can act with SO13 and any point can be mapped to any other point. If we restrict it so that it's the proper orthochronous Lorentz transformations, because this is actually the Lorentz group, then I need only worry about this upper hyperboloid. And again, we can quotient out by SO3 rotations to give me the hyperbolic space. And this will be a space of constant curvature, of course, because every point looks like every other point. Finally, we can look at the Euclidean space E3, which has metric ds squared is equal to dr squared plus r squared d theta squared plus sine squared theta d phi squared. Now in the case of S3, I'm going to make a change of variables to this equation. I'm going to write kappa r is equal to sine kappa big R. Let's move it over the other side. Then so dr is cos kappa r dr. So you get a cos squared kappa r over 1 minus sine squared. So that just gives me ds squared is equal to dr squared plus kappa to the minus 2 sine squared kappa r d theta squared plus sine squared theta d phi squared. I've introduced this factor here because when r is 0, I want this to be approximately, r is approximately r at some values, actually more rigorously. That thing tends to 1 as r goes to 0, which means that there's no conical defect. For H3, I'm going to make a similar sort of transformation, but it will be hyperbolic. In this case, I have the sinh, then 1 plus sinh squared is cos squared, dr is cos kappa r dr, so again we get ds squared is dr squared plus, I'll rearrange that, kappa to the minus 2 sine squared kappa r d theta squared plus sine squared theta d phi squared. And the Euclidean space, just r equals r, so ds squared is dr squared plus r squared d theta squared sine squared theta d phi squared. For the Euclidean space, you have the Euclidean group acting on the space, and you can quotient out by the rotations again to get the three-dimensional plane. Now, the metrics that we have, if I write k now instead of kappa, so that's going to be plus or minus kappa to the minus 2, plus 2 actually, then our metrics will all of the form dr squared over 1 minus k r squared plus r squared d theta squared plus sine squared theta d phi squared. We will either get, if k equals 0, we'll get the Euclidean space. If k is negative, we'll get the hyperbolic space, and if k is positive, we will get the case of S3, the 3-sphere. What we're going to do next is show that these are the only possibilities if we want a space which is both homogeneous and isotropic. So what we're going to do is prove the equation of geodesic deviation. So we're going to have a family of curves. This is xa of s and t, where these are geodesics. So let u be d by ds be the vector tangent to the geodesics, and s is distance along the curve, so it's an affine parameterization. Let z be d by dt, then the commutator z nu is 0 by the symmetry of mixed partial derivatives. So the Lie derivative of z is 0, or u dot partial z is z dot partial u. Now we can actually write that as z dot del u. Well, we've replaced partial derivatives by covariant derivatives. If you write this out in terms of Christoffel symbols, you get an extra term on this side and an extra term on this side, and they're identical by the symmetry of the Christoffel symbols in the lower derivatives. Okay, well let's work out u dot del squared za, and that's, I can write as d2za by ds squared. So that's u dot del of u dot del z, so that's z dot del u, eighth component, and that's u dot del acting on the z, which I can write as z dot del u, and that's got to be dotted in with the gradient ua, and then we have to write that in index notation. So we get this thing acting on that, so get del b and then u dot del u a. So I got that wrong. We're not differentiating that, but we get a u dot del grad b u a. It's better. So that z dot gradient. We're going to make this z dot del act not only on this u, but make it act on that whole thing. So that's u dot del u a. If I do that, I get an extra term which I don't want. So that's minus zb u uc del b del c u a, and this term is zb u c del c del b u a. That vanishes because u dot del u is 0. It's a geodesic which is affinely parameterized. So I get zbuc into del b del c u, actually let's put that at the end, del c del b u a, and that's minus r a d b c u c u d z b, which is the result I wanted to prove. Okay, so I'll just point out that R here was the Riemann tensor. Okay, now suppose we have a 3 space which is isotropic and homogeneous. Let's pick an origin arbitrarily and write the metric as ds squared as dr squared plus some function of r squared d theta squared plus sine squared theta d phi squared. So this follows from the fact that it's a spherically symmetric space, and here we'll have f of r greater than or equal to 0 and f of r over r tending to 1 as r goes to 0. Otherwise we would have a conical singularity if theta and phi take their usual ranges of values. So if theta and phi are constant, so that's a radial ray coming out of the origin, then this is a geodesic with affine parameter r. Now r a d b c u c u d z b, this has to be isotropic because the whole space is isotropic. So let's write as j delta a d g b c plus k delta a b g c d plus l delta a c g b d. And we're going to assume that u dot z is 0. So, and I need the u c u d z b here. A and D, this has B and C, so that's contracted, that gives nothing. I think this one also gives nothing, that has B and D contracted, yes. And here we are just going to be left with K times, well, UA UC is equal to 1 because it's affinely parameterized, so we're just going to get that thing there. And therefore, it's the equation of geodesic deviation. This equation here is d2 za by dr squared is minus k za. So we're going to take z actually as d by d phi in this case here. The Christoffel symbol is half g phi phi times dr g phi phi plus d phi g phi r minus d phi g phi r. Those are 0 anyway, but they would have cancelled. G phi phi is f squared g phi phi inverse is f to the minus 2. So that's f to the minus 2 half dr of f squared, which is 1 over f d by dr of f. Let's just write that as f prime over f. And therefore, u dot del, I should have said perhaps also that u is d by dr. So that's going to be u dot del. So that's the partial derivative plus f prime of r over r w phi. That comes from this Christoffel symbol. There's no contribution from any of the other Christoffel symbols. So that's 1 over, so that's just the same thing as d by dr. That's 1 over f d by dr w phi. So that's for any w which only has a phi component. Now, if we write w phi as u dot del z, or w is u dot del z, then you can check that this will satisfy these conditions, and since z also satisfies the condition up here, we get that d2 z phi by dr squared is u dot del squared z phi is 1 over f d2f by dr squared, and that thing was equal to minus kappa times z phi. Z phi is just 1, of course. So we have 1 over f double prime is minus k plus 1 pi 3 by f. So the solution is if k equals 0, then f has to be equal to r. Remember, we have this condition up here, which means that f must vanish at the origin, and this ratio gives me the scale. If it's kappa to the minus 2, so that's positive, then we get f is equal to kappa to the minus 1 sine kappa r, and if k is minus kappa to the minus 2, which is less than 0, then f is kappa to the minus 1 sine kappa r. And of course, if I put those particular expressions into here, I get the 3 spaces that I had before. I get E3 here, I get S3 and H3 again. So what we have shown is that the only homogeneous isotropic spaces in 3 dimensions are these 3 spaces that we have been talking about, and we have a very good idea about the geometric properties because we have represented them as embeddings in higher dimensional spaces. Next, it will prove useful to put these metrics in isotropic coordinates. So we're going to write ds squared as dr squared over 1 minus kr squared plus r squared d theta squared plus sine squared theta d phi squared. And let's write it as omega squared times dr squared plus r squared times d theta squared plus sine squared theta d phi squared. I can rescale r, and I can compensate for that rescaling by rescaling omega. So without this generality, I can have omega naught is equal to 1. And again, I don't want a conical singularity, so theta will range between 0 and pi, and phi will range between 0 and 2 pi. So equating the terms multiplying d theta, for instance, we're going to get omega r is little r, and for this term here I'll need omega dr is dr over root 1 minus kr squared. I can divide one by the other and I get dr over r, let's integrate that, which is log r over r naught for some constant r naught, which we will have to work out later, is the integral here. Let me set little r to be k to the minus a half times sine alpha. Then this thing will become 1 minus sine squared, so that's cos squared. The square root makes it a cos. The differential of this will give me a cos, and that r will then just give me a cosec in here. This factor here will cancel off from the dr and r, so all I'm left with is the integral of cosec alpha d alpha. That's minus log cosec plus cot. And there's constant integration, but I've already accounted for that over here. So what we find is that that's minus log sine alpha 1 plus cos alpha. So you can get r naught sine alpha over 1 plus cos alpha. Then omega, we get from this equation, that's going to be k to the minus a half r naught to the minus 1 plus cos alpha. I wanted omega of 0 to be 1, so that's when alpha equals 0, so that becomes 2, so I'm going to have to take r naught to be 2k to the minus a half. Now let's just construct the following, because I know it's useful. A quarter kr squared. So a quarter r naught squared k sine squared over 1 plus cos alpha squared. We know that from this equation we're going to end up with sine squared alpha over 1 plus cos alpha squared. So 1 plus a quarter kr squared is 1 plus 2 cos alpha plus cos squared alpha plus sine squared alpha all over 1 plus cos alpha all squared, but cos squared plus sine squared is 1. And I've got to factor 1 plus cos alpha, that's 2 over 1 plus cos. And we see that that thing from here, that's a half into 1 plus cos alpha, which of course is also cos squared alpha over 2. We're not using that. That's 1 over omega. So ds squared then, substituting all this in, is going to be equal to dx squared over 1 plus a quarter kx squared all squared, where x are now ordinary Cartesian coordinates. So that dx squared is then dr squared plus r squared d theta squared plus sine squared theta d phi squared. In other words, that is dx squared. Okay, when I went through this, I was assuming that k was greater than 0. Now you can do the same thing for k less than 0, but you'll get hyperbolic functions here, but you end up with exactly the same expression here. And that's not surprising because it's just really analytic continuation. In the case when k equals 0, ds squared is dx squared. The next thing we will do is consider an isotropic homogeneous space-time. So we're putting time into it now. And ds squared then is minus c squared dt squared plus a of t squared times the metric we've just found for the 3 space. So what we've done is considered k being constants. In the case for k greater than 0, this would be a sphere, which we have then expanded by a factor of a, and all the distances measured on the sphere have been multiplied by this function here. Had we wanted to, what we could have done is gone right back to this construction here and allowed this to depend on time. Had I done so, when I worked out the derivatives, I would get extra terms here and extra terms in here involving dt. So I really would have had to embed it in a larger space with an extra time component. So it would be a Lorentzian 5-dimensional space. Had I done that, I would have ended up with this thing with a k depending on t, but I'll get some extra cross terms in here. What I could then do is replace this term here by a new variable, say capital K y squared, which would then have no explicit time dependence. Had I done that, then the terms I get when I do my transformation of coordinates would exactly cancel off the cross terms I would have got from earlier on. So this actually is the quick way of getting to the answer, but I could have done it by considering time dependence throughout the computation. Now you might notice that there is no dx dt terms. Well, if you had a dx dt term, perhaps an n here, then n would define a particular direction, but since this space is isotropic, there is no preferred direction. So n would have to be 0, so you don't get any terms like that. You could have an arbitrary function of time here, but then all I've got to do is redefine my time coordinate to write that as a total derivative, and then I end up back with this expression here. Now, the next thing I'm going to do is work out the Einstein equations for this metric and suitable matter content. So I'm going to introduce the basis of orthonormal forms. So E0 I'm going to write as c dt, and EI I'm going to write as a dxi over f, where f is 1 plus a quarter kx squared. F at the origin is 1, and the gradient of f, let's write the partial derivative of f, is all 0 at the origin. What we're going to do is work out the Einstein equations at the origin. By the homogeneity property, that will be the same everywhere else, and that just simplifies the calculation. So we're going to use Cartan structural equations. So TE0, exterior derivative of that is 0, and that's going to be to minus omega naught I wedge EI, where this is the connection 1 form. DEI is AI dot dt wedge d over that. That's taking the derivative of that. I have to take the derivative of this thing, so I can have minus f squared when we, again, a k xj to this dxj wedge dxi, and that's minus omega I0 wedge E0 minus omega ij wedge ej. Now we need these conditions because the connection 1 form should satisfy this condition when I lower both indices, and the metric here is minus 1, 1, 1. So I can write down the solutions to this. They're pretty easy to spot. That's going to be a dot over c dxi. That certainly works for there, and for there you're putting values for ei in there. So that gives me, so this is at the origin when f is 1. So that gives me a dot over ca times ei. Omega ij is 0 at the origin. We'll have, actually I've jumped ahead. Let's not do it at the origin just yet. It's a little bit. Omega naught I is a dot over c f, so I'm not setting f to be 1 at this point. And omega ij is kxi dxj minus xj dxi over 2f, and we can just check that. So if I wedge it with ei, which is proportional to dxi, that gives 0. In this one here, remember that there's no sign change, so we end up with an a dot. We have a c which will cancel off when I substitute in from here. I have the f, and that gives me a t. The minus sign moves, swaps these over, so it gives me that term. This term you can see is going to work from here. You're going to get the xj dxi, that gives me that thing. And these are the extra terms which come in. So at x equals 0, omega naught I is a dot over c dxi is a dot over ca ei. Omega ij is 0 because x is 0, there and there. D omega naught I, we're going to get a double dot over c times dt wedge dxi, which is a double dot over ca times ei, e naught wedge ei, d omega ij, that's easy, that's k dxi wedge dxj, which is kei wedge ej. If a squared, remember we're setting f to be equal to 1 at that point. Well, these allow me to read off the components of the Riemann tensor. First of all, let's construct the curvature. Omega naught I is d omega naught I. There are no other terms contributing. Omega ij is d omega ij plus omega I0, which omega that. And that's going to be kei wedge ej over a squared plus this thing we get from those things, that's a dot squared over c squared a squared ei wedge ej. And therefore we can read off the components of the Riemann tensor because Rij, or AB, let's make it, is going to be half R A B C D E C wedge ED. So R naught I naught I is a double dot over A C squared, there's no sum over I there. And R Ij is k over a squared plus a dot squared over c squared a squared, c squared a squared, and that's no sum over I, no sum over j, and of course I not equal to j. If I equals j, then by the antisymmetry this is 0. We can work out the scalar curvature. Before I do that, let's work out R naught naught, And that's just given by contracting over the three values of I here. We have to lower this, so that gives me a minus 3 a double dot over a c squared. Rij, remember Rij will have to be proportional to the unit matrix by isotropy. There should be no eigenvectors of this matrix, otherwise they are preferred directions, and there are no preferred directions if it's isotropic. So what I need to do is add this term here, a double dot over a c squared, plus where I contract over j, and there are two values because we don't include I equals j, 2k over a squared plus a dot squared over c squared a squared, again with a 2, times delta ij. So the Ricci scalar is going to be minus that thing plus 3 times that thing. So that's 6 a double dot over a c squared plus k over a squared plus a dot squared over c squared a squared. That's my value for the Ricci scalar. Now T00 we're going to take to be rho c squared. So rho is the mass density. Tij is going to be the pressure times delta ij. So we have an isotropic pressure. Now R00 is equal to 8 pi g over c to the 4 times T00 plus a half minus T00 plus Tii. That's just the trace reverse of R, and that term obviously comes from the Einstein equations. Putting the values in here, we're going to get half here, so we end up with 4 pi g. We have a rho c squared there plus 3p over c squared. Okay, and R00 we had somewhere, which is minus 3 a double dot over ac squared. So we end up with the equation a double dot over a is minus 4 pi g over 3 rho plus 3 p over c squared, and that's known as the Raychaudhuri equation. There's a second equation which we can get from looking at G00, which is part of the Einstein tensor. That's R00 plus a half r. Now we're using an orthonormal basis. And that's going to be 8 pi g T00 over c to the 4. So we were looking at, I should say R. So R00 was this thing, minus 3 a double dot over ac squared plus a half r. And that's 8 pi g rho c squared c to the 4. So that gives me that thing there. Of course, those things go, and that gives me a dot squared plus kc squared is 8 pi g rho a squared over 3, and that's known as the Friedmann equation. If you want to put a cosmological constant in, then that's fine. But we can put it in as dark energy. An equation is state relating rho and p, so there's no loss in generality using that. Another thing we can do with this, if I take the logarithmic derivative of this, I get rho dot over rho plus 2a dot over a is 2a dot a double dot over a dot squared plus kc squared. So therefore rho dot is minus 2a dot over a rho plus, well, I'm going to substitute for a double dot from the Raychaudhuri equation. So I'm going to get 8 pi g over 3 rho plus 3p over c squared a, so a dot there, divided by that thing which I already know is 8 pi g over 3 rho a squared. Now I was multiplying through by an extra rho as well, so that can go. Those go. So we have rho dot is minus 3a dot over a rho plus p over c squared. And that's called the fluid conservation equation. This also follows from the Bianchi identity. So GAB semicolon B is 0, or equivalently TAB semicolon B is 0, well, particularly that one actually. Okay, so what we have done is used general relativity to work out the Einstein equations for an isotropic homogeneous space-time and found that we get the Friedmann equation and the Raychaudhuri equation. Now it turns out we can get the same answers if we consider Newtonian cosmology. And this is rather simpler. So what we're going to do is assume points in the space can be written R as scale factor times x. Are particles that just move according to this rule here, with x being constant. So let's consider a ball of gas or other sort of matter, and we're going to have a point on the boundary of this ball, and it extends out here, but we're just considering this thing here. Half mr dot square is kinetic energy. The mass within the volume is 4/3 pi r cubed times the density rho. Gmm over mod r is the potential energy by Newton's shell theorem, which shows that the gravitational attraction for a spherically symmetric system is given by the same formula as though all the mass was concentrated at the centre. Now there is a slight problem here, but I'll get onto that later. Now that gives me a half mx squared into a dot squared, that's the first term. Substituting this thing in here, that gives me an 8 pi over 3 a g, a rho and an a squared. And we're going to set this equal to a constant. I'm going to write the constant as a half mk tilde c squared x squared, because then this k tilde will match up rather nicely with the value of k earlier on. So I can cancel out the m's, x squared, halves, and I get the equation a dot squared plus k tilde c squared is 8 pi g rho a squared over 3. And that's the Friedmann equation. However, k tilde here is some sort of energy, whereas in the relativistic case it was the scalar curvature parameter. To proceed, let us use the first law of thermodynamics. So dE is Tds. We're considering a case where ds is 0. There's no change in entropy, so it's an adiabatic change we're looking at. that's rho c squared v. Rho is the density, so that gives me the mass. This is just E equals mc squared. And that's equal to minus p dv. So let's just write that out. That gives me, well, let's divide through by time. That says rho dot c squared v. So rho c squared v dot is minus p v dot. Now volumes are proportional to a cubed, so v dot over v is 3a dot over a. So rho dot is minus v dot over v into rho plus p over c. That's p. Minus 3a dot over a rho plus p over c. That's squared. So again, that's the fluid conservation equation that we had here. So now what I can do is take the Friedmann equation and differentiate it. That gets rid of this k tilde term. So we end up with 2a dot a double dot is 8 pi g over 3 times rho dot a squared plus 2 rho a dot. That goes. We're going to substitute in for divide through by a dot. 4 pi g over 3 minus 3 over a squared, so that's minus 3a into rho plus p over c squared plus 2 rho a. So that gives me minus 4 pi g over 3 rho plus 3p over c squared times a, and again that's the Raychaudhuri equation. So we get identical results whether we are considering Newtonian theory or we are considering relativistic theory. Right, now let's try and explain why these gave the same results. Let's go back to the metric, which is the Friedmann-Robertson-Walker metric. Writing capital X now. Okay, well, this metric can be embedded in a one-parameter family of metrics indexed by the parameter lambda, which is ds squared is minus c squared lambda squared dt squared plus a of t squared d little x squared now over 1 plus a quarter k lambda to the minus 2x squared squared. So in particular, if you take lambda equal to 1 and x equal little x, then you have the same metric. Now what I can do is write little x is lambda big X in here, and I'll get a lambda squared big X in here, and this thing will just turn into the same thing as we have here. So I just get lambda squared into minus c squared dt squared plus a squared d capital X squared over 1 plus a quarter k x squared squared, which means it is a constant conformal rescaling of the metric. The Ricci tensors, perhaps I'll call that R lambda, R lambda AB is lambda to the minus 1 RAB, and that corresponds to the case when lambda equals 1. You can see this because the Christoffel symbols are half g something up here, d something g down here. if I rescale G by a constant scalar, then the Christoffel symbols don't change. So therefore, R, A, B, C, D is invariant under that scaling. So if I contract on A and B, then this thing would be R, B, D would be invariant under scaling. And so if I raise them using the appropriate metric, I have to use the metric which is lambda dependent here to raise the index A. I have to use the one without lambda here, one with lambda equal 1 if you like, to raise this one here, and that's where this factor of lambda minus 2 comes from. We only need to investigate the Einstein equations in the neighbourhood of capital X equals 0, because the space is homogeneous, and so we'll get the same answers wherever we look at it. So R lambda AB is lambda to the minus 2 RAB, and that's lambda to the minus 2 times 8 pi G over C to the 4 TAB minus a half TCC delta A B, just from the Einstein equations, or written in a trace reverse way. TAB is the diagonal matrix, which is minus rho C squared P P P, and that will give me R lambda TT. I'm lowering the index here and taking A and B both to be time. I'll get a lambda minus 2 8 pi G over C to the 4 GTT with a lambda which is minus C squared lambda squared times rho C squared minus 1 times minus a half rho minus rho C squared plus 3p in there. That's going to give me, well, the lambdas are going to cancel off. We've got a factor of a half, which I can, as I get 4 pi G I get a 3, that should be a plus because I lowered it, 2, and that should be plus, rho plus 3p over C squared. Should be that way around. Because I'm looking at the TT component, which has the minus sign. R lambda TI is 0 by isotropy. R lambda IJ, well, we put IJ in here and we're using the TX coordinate system now, rather than the capital X one. So we're going to get 4 pi G rho C squared minus P when you put it into here. A squared delta IJ C to the 4 lambda squared into 1 plus a quarter K lambda minus 2 X bar squared squared. So this just comes from the components of the metric, which are here. So that bit there is just from that thing there, and the rest of it was from what I had before. Well, you can see as lambda goes to infinity, that thing goes to 0 at fixed little x. What happens to the metric in this net? Well, if I let lambda go to infinity, this thing, just this bit here, dr lambda squared, so that bit, will tend to a of t squared dx squared, and dr lambda by dt for light rays, so we're looking at ds lambda squared equals 0, so that will just be in magnitude c lambda, that goes off to infinity. So the null rays move in this metric at infinite speed. That corresponds to our Newtonian limit. So what we've shown is that the Einstein equations are preserved as for each value of lambda they give exactly the same set of equations because of this result here. You cancel off the lambda minus 2 when you actually is because of that thing. And so when you construct the Einstein tensor from this and you set it equal to the matter content, you get exactly the same equations independent of lambda. And that also means A, your scale factor, is independent of lambda, which is important. We might also notice that you could, if you wanted to, rescale A by a lambda dependent function, but we can always get rid of that by coordinate change. So you'll see that all of these equations, the Raychaudhuri equation, for instance, the Friedmann equation, if I divide through by A and I rescale K as well, I suppose, then the absolute scale of A does not matter. Okay, finally, there was a slight issue with the Newtonian calculation. It goes back to that. And that was that Newton's shell theorem doesn't really apply if you have an infinite mass distribution, which we generally have here. Instead, what we can do is reformulate Newtonian theory as a metric theory, and this is known as Newton-Cartan theory. So what you have there is a spatial metric, a time-like metric, both of which are degenerate, and a connection. The geodesics in this connection correspond to the motion of particles under free fall. So that would be a better way of doing it. What we can do is go back to the Friedmann-Robertson-Walker metrics and take V to be d by dt, a family of time-like geodesics. The equation of geodesic deviation is now this thing here, where E lambda AB is minus R lambda A C D B V C V D. This has to be isotropic, so this has to be proportional to the unit matrix. So if I were to contract on A and B, I would just get R T T with a third delta A B. That's what I need for consistency with contraction. There should be a minus sign there. Now, let's take Z to be d by dx alpha for a fixed alpha. So it could be d by dx, d by dy, or d by dz. I can work out the Christoffel symbol. We get that thing there. Remember, I is a spatial coordinate. This is going to be 0 unless I equals j. So we can work this out from the metric which we're using, this metric here. So the GII component, or let's say GIJ, is a squared delta ij over 1 plus a quarter k x squared squared. Obviously the only time dependence I have here is given by, let's just write this out, dt GII delta I j, no summation over I. So that gives me a half a to the minus 2 dt a squared, which is a dot over a times delta ij. And rather similar to what we did earlier on, dza by dt is partial dza by dt plus a dot over a za. That's the Christoffel term. Here, if you write it out in detail, we're assuming that, well, we know that za is proportional to delta a alpha. In fact, it's equal to that thing. And even if it's just proportional to it, then we still have this result here. So if we do it twice, and you can check that there are no other components which come in because of various Christoffel symbols. We're evaluating this at x equals 0 to make things easy for ourselves. Of course, that thing is 1 over a d by dt of a za. So if I do it twice, and put this thing in here, I'm going to get that d2z a by dt squared is a double dot over a for each alpha. And I suppose I should write it like that. Let's go back to the equation of geodesic deviation. This equation here, I end up with a double dot over a is equal to minus a third RTT. And that thing is delta AB on both sides, which I've cancelled out. So RTT, we had a formula for that. It's this thing. It doesn't actually depend on lambda. Minus 4 pi g over 3 rho plus 3p over c squared. So you can see that again is the Raychaudhuri equation. And of course, this was done in general relativity, but we can perform this calculation in the Newtonian space-time. This quantity here shows that this equation is available to us in the Newtonian space-time. Obviously, we can integrate this up once while assuming the fluid conservation equation in order to get the Friedmann equation. So that's a way to tie all these things together. So what's really going on? What we have done is considered a conformal family of metrics, and because they're conformal, we can very easily write down a relationship between their Einstein tensors and their Ricci tensors. They're just simple scalings. It finds that in this case the Einstein equations are preserved for every member of that family. If we go into different coordinates, ones which are scaled, then we find we end up, as lambda goes to infinity, with Newtonian space-time, which will therefore have a solution in terms of A being the same as the solution for all other members of that family. So that shows why there are no general relativistic corrections to the Newtonian result. What we have managed to do is discover the reason behind the result of Milne and McCrea. In our method, we have played one set of coordinates off against another. In one set, the metrics are conformal, where we identify points on different manifolds by the requirement their coordinates are identical. After making a change of coordinates on one of those manifolds, in fact a lambda-dependent change of coordinates, the metrics are no longer conformal. What we've done is work out the Einstein equations and show they are preserved. The point is that the homogeneity of the solutions mean that it doesn't matter where we work out the Einstein equations, and thus we can do a change of coordinates without changing the Einstein equations. Another way of looking at this is to argue that we have blown up a small neighbourhood of the origin in such a way that the Einstein equations are preserved. In this limit, the scalar curvature goes to 0 and the speed of light goes to infinity. This is our Newtonian limit. Moreover, in this limit, the scale factor is preserved, and thus the scale factor from the relativistic theory is a solution of the non-relativistic theory. In other words, the Friedmann and Raychaudhuri equations derived from Newtonian cosmology are identical to those from the relativistic theory, and that was what we wished to prove.